Hi, my name is Ryan Lamazaris, and this is my Lab 5 report. To start things off, the goal of this experiment is to measure the time it takes for a bar magnet to fall through a tube. In this case, it's going to be an aluminum foil tube. And then we have to observe the interactions between the falling magnet and the aluminum foil. Before we start the experiment, you have to have a couple measurements, as well as you have to determine where the north pole of the magnet points. For the measurements, you need the dimensions of the aluminum foil, as well as the mu value you got from last lab. So some of the fundamental principles used in this experiment revolves around Faraday's law, specifically curly E fields and induced current. For the curly E fields, the change in flux has to be increasing downwards, since the mu value is also going to point downwards as it's falling. And from that, the negative change in flux is going to point upwards. Based on the right-hand rule for curly E fields, your thumb points upwards in the negative change in flux, and your fingers will curl around the aluminum foil tube. In this case, the curly E field will be in the counterclockwise direction. From the curly E field, you can deduce that the induced current is going to counteract the acceleration or velocity of the falling bar magnet. And from this, the total net force is going to be the gravitational force of the falling bar magnet, as well as the magnetic force created by the magnet to counteract it falling. So some of the data that was measured is the mu value from last lab was to be 1.86. That's in amperes times meters squared. And then the dimension of the aluminum tube is 30 centimeters, 5 centimeters, and 1.25 centimeters, with the length, width, and inner radius being labeled in the picture to the right. After conducting this experiment 5 times, the average of the time it takes for the falling bar magnet to fall completely through the tube is just over 2.5 seconds. So some of the what ifs in this experiment is, what if the resistivity of the conductor was close to 0? Now, if the conductor was close to 0 for a resistivity, then the magnet would be incredibly close to falling as if there was no conductor there. So in this case, instead of 2.5 seconds, it'll fall the same distance in about a quarter second. Then, what if there were holes or cuts in the tube? If there were holes and cuts in the tube, the velocity of the falling magnet would not be constant. And this will be evident in the next slide with the graphic of the code, but the cuts in the tube will allow the magnet to have no induced current for a brief amount of time, which will speed it up very slightly. Moving on to the coding section of the lab, you have the final graphic of what happens if the codes run correctly. The large flat line run across the graph is just saying that the bar magnet falls with a constant velocity through the aluminum foil tube. And after plugging in all the measurements, the time in the tube is 2.3 seconds. Step 1 of this experiment is more or less putting in all the measurements and dimensions of the aluminum foil tube, as well as the mu value for the bar magnet. Steps 2 and 3 are two defining functions. For step 2, the defining function is the magnetic field of a dipole, or a magnetic dipole, so the bar magnet. And then the defining function for step 3 is calculating the change in flux of the falling magnet. The while loop just helps simulate the bar falling down. And steps 4 to 8 are kind of mixed together and in between each other. So the main gist of here is there's a big for loop running over and over and over, which adds the total force of the gravitational force as well as the magnetic force to get one force net on the magnet. That is it for my live report. Thank you.